Welcome back. In this lecture, we will discuss k-means clustering. Here are the objectives for this lecture. So, some basics. So, k-means is a partitional clustering algorithm, meaning given a set of samples where you have associated features with them, it's going to group those samples into k disjoint clusters. And so the input is very simple. We're going to assume that there are m number of samples and the natural number k, and the output k partitions of the m samples, and each partition will have a centroid. Now, a centroid is just a coordinate in the feature space that's the center for each cluster. It does not necessarily have to be associated with any of the samples. So here's the algorithm. So first is initialization. Pick k points in the feature space, and we're going to label these points as C1 through k. These are the centroids, and they will iteratively be updated in the algorithm. Now, picking the initial points, sometimes it's just done totally randomly at anything in the feature space. Sometimes it's done in a way where it's distributing the k points uniformly in the feature space, or sometimes it's done by selecting coordinates associated with samples in the data that we're looking to cluster. But regardless, some method you're going to pick these k points, and oftentimes the method that is used is almost like a hyperparameter. It's one of these things that you'd want to experiment with a bit, and it may even involve domain knowledge. So 2 is, while a stopping criteria is not met, we're going to do the following. Now, in a little bit later in the lecture, we'll discuss what the stopping criteria is, but for now, we're just going to say there's some criteria that has to be met for it to stop. So for each of the samples, we're going to do the following. We're going to look at each of the centroids and compute the distance between each sample and each of the centroids. So we have all these distances, and then we're going to assign each sample xi to a cluster j, that is associated with centroid j, where the distance between x and centroid j is smallest. So that makes a lot of sense, right? You have the centroids, you have the samples, you have a distance function that's, again, one of these kind of hyperparameter things that you may or may not need to optimize a bit. And you just take the, at a given iteration, whatever centroid that sample is closest to, it gets put in that cluster. Now what you do is you recompute the centroids, and the centroids are based on the new clusters that you have. So you have all new centroids, and this is now what leads to going back to the top of the loop. Once you compute those centroids, you could check that against the stopping criteria, and if it's not met, now you're going to go again through all your samples and compare the samples to the centroids and assign two clusters and recreate centroids. Now let's look at some common stopping criteria. So first, one way to stop the k-means algorithm is to look at when the number of reassignments of samples to clusters is below a certain threshold. So if on a given iteration I'm only assigning 2 or 3 samples to a different cluster than they were in the last iteration, maybe that's not enough to continue on, especially as you have large amounts of data, a very small number of things being reassigned, then that is good enough to have a nice set of clusters. Another stopping criteria is there's no change in centroids. So if the centroids aren't changing, effectively your clusters aren't going to really change either. Finally, there is the minimum decrease in the sum of squared error. And so what you're looking at is for each cluster, summing over the distances of the samples within that cluster to that cluster centroid. And so if you have a lot of things outside of a cluster or a lot of things in a given cluster that are actually closer to a different centroid, that's going to be a further distance away from the centroid it was assigned to, thus increasing the error. So here's a little example. So here's a group of points in a two-feature space. And we start out, we just pick two of the points, but they don't have to be samples. They could just be any points in the feature space, and we're going to say these are the centroids. And from that, we compute for each sample in the data set, we compute the distance to the nearest centroid, and it gets assigned to a cluster for that centroid. So this is what we've got. So now that we've got these initial clusters, we will find new centroids. And here they are. And so we will now recompute distances from all points in those clusters to the new centroids and reassign. And we get this. So now we will, again, compute new centroids since we have new clusters. And now see the centroids just moved a little bit. But now here, when we recompute distances from points to centroids, none of the points move to a new cluster. So, we've probably reached the convergence criteria depending on what we put. So what are some nice things about k-means? Well, one is really quite quick. The time complexity is OTN, where T is the number of iterations, K is the number of clusters, and N is the number of samples. Most people consider it linear time because K and T are often much smaller than your number of samples. There's a whole lot of implementations out there. Every major machine learning toolkit has a k-means implementation. And it finds a local optima if the sum of the squared errors is used. Weaknesses of k-means? Well, you need to define k. There's a couple methods for doing this, such as the elbow method that I think is in one of our exercises. K-means is also sensitive to outliers, and we'll show a visualization of what that means. And the computation of centroids must be defined. And so this can get quite difficult. So there's, in certain cases, there's kind of a clear geometric interpretation if all the features are scaled the same way, for recomputing the centroids. But this might be difficult to do if some of your features are, say, categorical. And the way you compute the centroids might also have to be something you would need to consider in certain domains where you have maybe some very special types of features. And just on the outlier sensitivity, this is an example of something that happens. So if k equals 2, you have these two clusters, but just visually looking at this, that point that's off to the far right, probably doesn't belong in either of those other clusters. But he gets put there, and the centroid gets positioned in a certain way because of how the algorithm works. And so, there are techniques to help kind of reduce this problem, especially in determining the number k. So I hope you enjoyed the lecture. Stay tuned for more content.